All right, good morning, everybody.
So.
It's my distinct pleasure to welcome Professor Harald Hillebrecht as a seminar speaker this morning. He began his studies of chemistry at the University of Freiburg in 1981 and completed his PhD there on halides of molybdenum and platinum metals in 1991 with Gerhard Thiele, then of course also University of Freiburg. Then he moved to the Max Planck Institute for Solid State Research in Stuttgart, working with Professor Hans-Georg von Schneering from 1991 to 1993. And then, this is a common feature, he moved back to the University of Freiburg for his habilitation 1993 to 1997, and then he became a professor of solid state chemistry at the University of Bonn. For a few years, in 1999, he already moved to the University of Bayreuth as a chair. And then in 2002, again back to the University of Freiburg as chair of solid state chemistry, where he was also then dean a few years later. His research continues to be on synthesis, structure, properties, as well as theory. In addition to being a highly successful professor, it's an interesting statement here, he's also a great athlete.
It's not here on the official CV.
Having done several Ironman and impressive stunts, such as flying to Sydney, dropping the luggage at the start line and running a marathon. When he visited us here in Waterloo in 2011, I have a really nice list here. We went kayaking on Lake Huron on Saturday and then moved to Mississauga to run a little race on Sunday morning. And this morning, I said, I have a great laptop here full of battery and stuff. So that's where all the photos are from Mississauga and Lake Huron, but now we're running out of time, so I can't show them now. Okay, please welcome Harald Hillebrecht for his seminar, Inorganic Energy Materials. It's all yours.
Thank you, Holger, for this special type of introduction. Thank you. You see, it's always a pleasure to come back on places where turned out to be good. One of them is Freiburg. Another one is Waterloo. Sure, some guys never leave Waterloo again when they came from Germany. Well, I've been here in 2011. I already gave a talk. I guess no one of you had been there. That doesn't matter. But Holger asked me to tell something different, so I will not talk about our main subject on research, boron and borides, and on another aspect. And the reason is that we are interested in an international graduate school together with Freiburg and Waterloo, McMaster. So maybe one of the students are potential users of this wonderful program, and the general idea is inorganic energy materials. What can we do from solid state chemistry in this direction? And that's why I introduce some of our aspects that are dealing with these topics. Well, materials and solids, it's a starting point where I always have a little bit of discussion, because as a solid state chemist we have a nice logo that means only solids are forever, if your Latin is a little bit gone. Nah? And I did it for 9 years, and one of the very, very few advantages is that I can translate something like that, but it's less or more useless. Nah? But now I know what it means, and it leads to the fact that we overemphasize the importance of material properties of solid compounds, because just to have a new compound which is a solid doesn't mean that we have a new material. There's a fundamental difference, and the difference is the way how we can use it for application in real systems. But nevertheless, as solid state chemists, we are chemists, so we produce new compounds and can try to improve properties, or it's another important aspect, I guess, improve synthetic processes. That how can we optimize experimental synthetic procedures, that things can be made easier, cheaper, better, whatever. That's, I guess, one of the topics that we can deal as a chemist. I hope you get my wonderful German English, and because I'm not used to talk in English, but hope you will survive. Well, I would like to explain our things with some case studies, and I'd like to reduce this word inorganic energy materials as materials for the energy conversion and storage. That means no catalysis, no heterogeneous catalysis, just the pure material as a bulk material for these two aspects. And I'll give you a short overview on things we do on several aspects for application. The first ones are thermoelectric materials, we have magnetocaloric materials, we have some materials which might be useful for capacitors, for battery materials, and finally, which is the biggest part, the very recently discovered halide perovskites for the disolar cell. Well, let me start with a very short, because I know it's also popular here in Waterloo, thermoelectrics. It's just the conversion of less or more waste heat into electrical current, and on the other hand, the transform of current to cooling purposes. And it's quite simple, especially for me as a chemist. You have a temperature gradient and you can use it for the generation of electric current, or vice versa. You can use a cooling device by current. The advantage is that you have no moving parts, you don't hear anything, nothing can be broken, and you don't need energy supply from a power station. You can generate the energy by yourself. That means it's energy autonomous. And that's a point which is sometimes for several aspects of application important, that you have an autonomous energy supply, and especially for sensoring and other things like that, it's important to have energy by your own. If you can use every temperature gradient for that, that's a quite funny thing. As you all know, electric and thermal conductivity are not independent, they are coupled by diverse physical laws. And one of the important curves is this one. That means the so-called ZT value, that's the holy grail of thermoelectrics. We should have a value about 1, about that, but don't care too much about it. Why did we start with these systems? We had a project on bismuth telluride, which is this representative here, and you see that around room temperature, bismuth telluride is one of the best material. And we developed a process which gave nanomaterials for the bismuth telluride, which worked quite well. And so we did, why can we skip the telluride, just do solid solutions for bismuth and antimony? And the idea is quite clear. At very, very low temperatures, around 100 Kelvin, it's the only good material for these very low temperature applications. And nobody wants to generate energy at these temperatures. Now we have the idea with the cooling device, and cooling to very low temperatures should be possible if we have quite good materials for that. Bismuth and antimony make a solid solution, that's not a problem, but the synthesis is usually done by mechanical alloying, and these processes are quite simple, but it's difficult to do a scale-up, because a mechanical alloying in upscaling is just you use several of the mills or larger mills, and that's not very good. And the doping is also a little bit a problem, and the production of a nanostructured material, which is important for the lattice part of the thermal conductivity, is very difficult to do it in a well-defined way by mechanical alloying. Well, we were able to synthesize the system with about 15% of antimony, which is the optimum for the ZT value, by a solvent-based process. And this is quite simple. We use the citrate of bismuth, the chloride of the antimony, and reduce it with aluminum in a polyethylene glycol solvent with water and chloric acid. This process we had developed, as already mentioned, for the bismuth telluride, and we were able to obtain well-defined nanoparticles, and we could show that we can produce a compact material for the thermoelectric application by the so-called spark plasma sintering technique. I'll explain it in more detail for the next topic, and that means that we can compress the system under applied pressure and temperature, and we could show that this process of densification keeps the nanostructure less or more unchanged. And that's important because of the thermal conductivity. And the ZT values that you obtained are comparable to the best ones. Our curve is the lilac one, and we see it's comparable to the best values which were published by other groups, and we could show that our process really results in quite uniform and homogeneous material, which is not so easy, but we were successful in that way. We have measured all the properties which are important for thermoelectrics, and we could show that we have an excellent thermal conductivity, which is a result of the nanostructured system. We have a quite a normal Seebeck coefficient, and we have a quite low electric conductivity. So this is a point where we should work on our process, and it is the weak point that we didn't get better values. I guess Holger was saying, yes, there's still some work to do. Well, we are doing that. One problem is the doping. Usually most of the material is an N-type material by itself, and that's what you see from the sign of the Seebeck value, that we have an N-type. And the problem is how to do the doping for the P-type, because for the application we need both. And now we are on a good way to do the doping with tin by a solution process. During the last 2 weeks, we had some important progress, so I will not talk about that. But another point is, when you do the compactation, you always have a problem with the porosity, but here we also are up to about 94% density, which is quite good to get reliable properties for the thermoelectric material. Second aspect, high temperature materials. There's one system, silicon germanium, which is also structurally quite simple because it's the elemental structure. We see there is a solid solution between germanium and silicon, so it looks quite simple, but it is not easy to get homogeneous material. And by the application of our pulse plasma synthesis, we were able to get homogeneous material of the solid solution, and especially for the high temperature processes, it's not too bad. Okay, there are some other systems which are better, but there is a fundamental problem in the measurement, in the reliable measurement of thermoelectric properties. If you look in Nature or Science or whatever, you always find a report which we have great values, but sometimes the values come from different measurements, and you combine the values in a way that you get a good number when you get it published in certain journals. Now, I will not give too much comments on it. So we have seen the need for a reliable reference for thermoelectric materials. And now it's an advantage that this solid solution is chemically very, very stable. And we know most of the values of silicon or doped silicon from solid-state physics. I guess there's no system on the world where we know more about this. So we know most of all the physical properties, and then was our idea that we can exclude the influence of the structure or of the microstructure, because it's always a part of the lattice thermal conductivity, and it's very, very difficult to get well-defined values for that. And so our idea was, we just grow a single crystal, and a single crystal has no influence of the microstructure because it is a single crystal, and we have a system which is chemically quite stable. So we put a part of this single crystal and can use it as a reference to validate all the ZT machines who measure these values. And this idea was developed together with one of our Fraunhofer institutes, and that's how we tried, no, we did, we realized it. That means we do a material by the SPS synthesis as a pellet. We combine several pellets to a feed rod. This is our machine where we have the SPS device in it, and we have a graphite device to compress it, and a pressure chamber. And we see that we can produce well densified pellets, and we combine several pellets to a feed rod, and after that we start the single crystal growth in a mirror furnace with elliptical setup. and do a floating zone single crystal growth, starting with these feed rods. And the general idea is to use well-defined pellets as a feed rod and to grow single crystals by the floating zone method. That works quite well. We had a starting material and we could show that there grows in fact a single crystal, and according to the separation and the different solubility of germanium in the solid and in the liquid state, we get a difference of the concentration according to the size or the distance to the starting material. That's a situation which is quite well described by the equation of Pfann, and you could see even the influence of a shift or change of the growing conditions is visible in the change of the germanium content. And when we could show that it works indeed with this Pfann's equation to get well-developed single crystals without further twinnings and others, we changed the process according to a zone leveling. That means we could estimate with which additional amount of germanium we should start. We could synthesize a pellet with the appropriate content of germanium, and starting with this modified feed rod, we were able to grow single crystals with a well-defined and nearly homogeneous content of germanium. It's one of the very first examples that we could grow single crystals of homogeneous solid solutions of silicon and germanium in that way. Well, a very short project. There's one compound, bismuth, copper, selenium oxide, which shows quite good thermoelectric properties at around 700 degrees Celsius. A CT value of 1.4 is not too bad, so it looks very promising, but there are some problems, like in real life. To synthesize it, you need a pre-reaction. That means you start with the raw material, grinding, pellet, pressing, and again in silica tubes. It's very, very difficult, and you get only small samples. It's not possible to do a scale-up in this technique. And so we tried to develop a one-pot strategy or a one-step synthesis, and indeed, starting with the ball milling of the raw material, we could do it within one step SPS samples at well-defined conditions, and we got homogeneous samples. The reason why it was necessary is seen here. If we look for the usual pellets, we see that there are lots of cracks, and it is not possible to get reliable data for the thermoelectric properties if you have cracks in your sample. So some of the data which were published, we don't know how they were produced, because you need a well-developed sample without inclusions and cracks and so on to get reliable values for the thermal conductivity. But we have changed our pressure device from graphite to steel, and then we could apply a higher pressure. And using this higher pressure, we were able to obtain very well-developed samples where we could measure the thermoelectric properties. But it took some time to design the process in a new way to correct for the thermal mass of the steel, but now we are able to do it in a proper way. That means we could control the temperature by additional thermocouples, but now we are in a quite good way. Okay, what else? In a collaboration with Yuri Moharisky, all these Ukrainian names are not so easy, but you know maybe who I mean. We had the idea to develop another technique for the conversion of current in cooling devices, and one is the magnetocaloric effect. That means the phase transition of a ferromagnetic material to the paramagnetic material is combined, like all phase transitions, to the exchange of enthalpy and entropy. And you can use the transition for a ferroelectric material for cooling devices, like you know it from the Linde process to solidify or liquefy the air and separate nitrogen and oxygen. So you do a cycled process where you combine a heating step and a cooling step. That means the energy which is produced by the phase transition can be put outside of the system, and if you relax the system, it takes the energy or the heat you have taken out from itself, so it cools down. And if you combine these two processes, it's possible to build a cooling device which has a comparable efficiency as we do it with the thermoelectric or Peltier systems. This was developed in the late 70s for gadolinium, but for this purpose you need superconductive magnets, so it's not a sensible method to get a cooling device. When in the mid-90s the giant magnetic resistance effect was the giant magnetocaloric effect was developed, was found. There were new materials which were also good candidates and which can be used in prototypes, but meanwhile, according to the high price of germanium, the most important systems are iron-based or phosphorus-based systems. Very recently there was a nice publication on a boride, and boron chemistry or borides, it's one of our center of competence that we have in our group. And at that time I had a master student in the group of Yuri, and he said to me, oh look, there is a nice idea what they have published, because this system or this compound has a Curie temperature around room temperature, and that means that you can use it for a magnetocaloric cooling device from room temperature to lower temperatures. And there we had lots of experience on these borides, and the idea is, can we do a substitution of the transition metal that we can decrease the Curie temperature but maintain the good magnetic properties. And this was not the case for manganese. It was possible to do the substitution, but the transition was very broad and so no more useful for magnetocaloric applications. And my master student was able to develop a process first by arc melting, later on by this pulse plasma synthesis, and she was able to substitute a part of the iron by cobalt, and we could show that we get a linear decrease of the Curie temperature by increasing cobalt content. And this is exactly the field where we can assume low temperature cooling application. That means around 200 K. That's the lower limit, which is sensible for technical application. And it's really a quite interesting development that we show that we had the linear dependency of the cobalt content to the Curie temperature. Another advantage of our SPS synthesis is that we get bulk material, which is easy to handle, which shows no cracks, and which can also show a continuous content of cobalt. That means we can also manage to get a gradient material. We could show that the magnetic entropy is less or more maintained, and the different size is just a different amount of the sample. That means the entropy for the process is nearly comparable for all different cobalt contents, and we also could show that the sharp transition is maintained for all the compositions. So we have a new material for application in magnetocalorics. Unfortunately, there are still some other materials which have a more pronounced effect, but nevertheless, our material is mechanically very, very stable. It is chemically very stable, so it's not a problem to use it in a device where you have very high forces when you do the cooling cycle. Well, we are solid-state scientists. We try to get some new samples. We were successful. Sarah Hirt, my master student, was able to synthesize a new compound. We are not sure is it a new material because up to now we have not yet measured the magnetocaloric properties. Nevertheless, I'm a chemist, so I'm proud to have a new butterfly, and so I'd like to explain the crystal structure. And as I'm a boron chemist, now I have to tell you this story. As we know it from all the transition metal borides, there are trigonal prisms around the boron with a transition metal, and as always, the sides are kept by other boron atoms to form boron-boron bonds, or by a second metal. And usually it's a high preference of the transition metal compared to metals like aluminum for the direct interaction between boron and the metal, and the aluminum metal prefers the capping sides. Now we could show that this composition is a quite simple structure derived from our first material here, because we see there's a complete series of these materials where we have the transition metal boride part and an intermetallic boride part. And some years ago we had a nice work on systematic variation of these ternary borides. You may see here our first example with a composition 1, 2, 1, 2 with a zigzag chains of the boron and the metals in between, and this is a fragment of a cubic body-centered packing. And by additional boron content, you just increase the size of the boron substructure by additional zigzag chains, or you can also increase the share of the intermetallic part as a BCC form. You see here we have one layer of intermetallics, here we have two intermetallic layers, and here we have three intermetallics. Just like a toy, you can just build it up. This building principle was generalized in this publication. And you see that this composition is very similar to what we had here, and we could show that the relation is quite simple. Starting from the simple compound with the zigzag chain, we cut out a part of the structure, do a shift, and bring it together again and get exactly the structure we had here. That means we just add an additional layer of an intermetallic part with the BCC characteristics. And so in contrast to this example where we had the layer parallel to the boride structure, here it is less or more perpendicular to the boron zigzag chains. And it was an idea we did not regard when we developed our building principles. Well, that's one idea to develop or to explain the crystal structure. Another idea is to remember that many intermetallics have a BCC, or if an ordered variant, cesium chloride structure. And that's another way how to explain this new structure. We can start from a cesium chloride type as a 3×2 supercell and substitute 2 of these cubes by 4 of the boron atoms. And it works quite well, and because trigonal prisms are no squares, you have to do a little fitting, so it's a little bit distorted, but nevertheless it works quite good. And some of our new compounds we have found, for example, this ruthenium compound is just an example for a 3×3 supercell. Now you have a larger share of the intermetallic part. That's quite clear because you have a different share of the you have a connection of the transition metal part because you have a higher share of the boron. And this continues a series that is known from other ternary transition metal borides. On the other hand, you also can remove the aluminium atom and you end up with a pure transition metal borides, and you see that the building units are exactly the same. So you can play around, and as a structural chemist, I like these things, although I know that they are not so really important for application. Second last field are the so-called max phases. These max phases are meanwhile quite famous, because in the late 90s it was shown for the titanium-3, silicon, carbon-2, that this is a very special type of ceramics, because the properties are a mixture, and in that case a positive mixture, of the high temperature stability of ceramics and the machinable properties of intermetallics. That means the cracking of ceramics is always a problem, and you can avoid these problems by the combination of the typical properties of alloys or metallic materials. No? And the explanation is quite simple, because you have both structural units within the crystal structure. You have one part which is a transition metal carbide part. This is so M and X, and you have one part which is an intermetallic part. No? And so we have a quite good explanation why we have a combination of both properties. So these ceramics were investigated in a very, very extended way for the use as ceramic material. But my question is, why single crystals? No? Because one explanation or one answer is because we can. No? So, but that's not the only explanation. The other is some of the investigations can or should be done based on single crystal data. One example are vacancies in the carbon positions. It is very well known that binary transition metal carbides are intrinsically non-stoichiometric. And we know that mechanical and especially physical properties depend from the non-stoichiometry. And so the idea is, if we have a ternary compound which shows this close similarity to the binaries, no? That means the increased content, according to N, the increased content of transition metal carbide is managed by an enlargement of the thickness of the layers, then we should expect the same phenomenon. We could show several years ago for the system with vanadium, aluminum and carbon that indeed there are ordered or disordered vacant sites for the carbon positions, and we could show that the stoichiometric composition is not stable, and very recent calculations and also measurements have shown that indeed the deficit is fundamental and necessary for the stability of these max phases. The other is we can modify the properties by substitution of the different transition metals and or main group metals and or non-metals. That means, according to the structural properties, it is clear that we can vary the transition metals when we exchange different early transition metals, when we exchange the main group metals or main group elements or the non-metals. Another point, why single crystals? We can measure micro hardness for the single crystals. If you try to model the physical properties, we know that we have strongly anisotropic behavior. That means the hardness, the formation processes are very, very different between the different directions. And it's quite easy to calculate it, but it is very difficult to measure it. And so you need the anisotropic properties of a single crystal to measure the anisotropic properties of the material. So that's possible, and we could show for the first example, no, to be true, the second example, that the hardness of the crystals is strongly anisotropic, about a factor of 2, similar to the values which were calculated. And another project we had in Freiburg was the question of corrosion, because if you try to use these ternary carbides for protection, lots of intermetallics are attacked by saline, by oxygen condition or oxidizing conditions, and then you may use these max phases as a layer for the protection. And now you have transport properties, for example, ions or what else were taken in or out, and so we had the idea to measure or to control these diffusion processes on the basis of single crystals, how the ions migrate in or out. That was a nice idea. Not yet, we are finished with the project, but later on there were some very interesting contributions from the large max phase society, and they could show that by a chemical delamination, that means by exposure to chlorine acid, you can remove a part or completely the main group elements from these two-dimensional systems. You see it from the pictures in the electron microscope that you get a delamination of these two-dimensional systems, and you have less or more something like graphene. And it was shown that these are interesting materials for the lithium battery, or they can be used as capacitors. And then it becomes again important how we can substitute these transition metals, the main group elements, because we have an influence on the delamination process according to the reactivity from the deintercalation. And we have an influence on the properties of the remaining transition metal carbide or transition metal carbide nitride layers. And that's why we guess it's important to investigate it in more detail. And some of these details I will show here. So we could grow single crystals from this system containing titanium, molybdenum, aluminum, and carbon. And based on the single crystal data, we could show that the structure is a disordered but a strong preference of different sites for the single crystals. And some of the data show that the carbon positions are completely occupied. We can conclude from the displacement parameters. And the picture I've shown here represents a probability of 99%. That means the thermal displacement parameters are less or more isotropic, and the size of the displacement parameters shows that we have no deficit on the carbon side, and we also have no deficit on the main group metal side. But we could show that we have a mixed occupation of the transition metal positions, and according to the composition, it's not absolutely equal. We have a strong preference of the inner position by the early transition metal titanium and a strong preference of the outer side by molybdenum. We can refine the occupation factors, and we see that we have a composition which is quite close to the composition we got by electron microscopy by EDX measurements. Nevertheless, we would expect a composition titanium 2, molybdenum 2, aluminum carbon 3 if we have complete occupation. If we have the same deviation, it would be maintained, but it's not the same, so you have a slight deviation. And we could show that also the so-called 3-to-1 phase shows this asymmetry. We have a strong preference of the inner side by titanium and of the outer side by molybdenum, but because the multiplicities are not the same, we have again a deviation. This is quite normal, less or more. We know that titanium carbide is much more stable than molybdenum carbide, and obviously we prefer the higher coordination of the transition metal by carbon. This is the coordination number 6 by titanium, and here we have only 3 molybdenum carbon contacts. This follows the well-known stability of the binary carbides. And for example, if you think about the use of these two-dimensional materials for catalytic processes or something like that, we can give you an idea how the transition metals prefer the different sites. Last point of my topic, it's one of the most exciting things we have actually in solid-state chemistry. About 5 years ago, there was a first report on, here in red, on perovskite-based solar cells. The old idea of a dye-sensitized solar cell was shown that it is a good idea, and they have started only about 5 years ago with the first reports. Only a few, no, I've excluded it. Only a few reports had been, and now more than 500,000 publications on this topic is done, and there is no issue of nature or science where there is not a contribution on these systems. During a few years, it was possible to increase the efficiency to a value above 20% if you compare the time which was needed to do it with other materials for the solar cell. You see the tremendous development. Now the idea is, this is methyl ammonium lead iodide. This is the so-called perovskite structure. So this is the perovskite solar cell. And it looks good, but lead is not the best metal you can use. So the part of the investigations is the substitution of lead by other main group or transition metals, the variation of the organic cation. These are so-called hybrid materials, organic, inorganic materials. But from the point of view as an inorganic chemist, I just laugh about the organic part of methyl ammonium. It's less or more inorganic. Nevertheless, I accept it. And the idea is to substitute the methyl ammonium by other organic, simple organic cations. Another idea would be to do a variation of the anion, or to change the structure a little bit. Maybe you know the story of the ceramic superconductors with the copper oxides. There it was the same story, that they tried to change the principles of the structure by additional metals, and you have this long series of so-called Waterloo phases where you combine the different constituents in different ratios. Well, what was our job, or what did we define as our job? Methyl ammonium lead iodide is great, but there are some disadvantages. One is the sensitivity to moisture. And one idea to solve this problem was the substitution of the organic cation by cesium or formamidinium, or to change, it must be an L, the halide. And it was shown that the addition of chlorine makes the sensitivity a little bit lower, but it has been shown that it is not the uptake of chlorine, but it changed the process of the deposition of the material. Then there is a phase transition of methyl PBE lead iodide around 50 degrees Celsius, and that's a problem because these are temperatures which are reached during the use of the solar cell, and that means you have an inherent instability of the microstructure of your layer, and it would be good to be a little bit outside. Third point, the lead compound is a 3D cubic perovskite. And in the first moment it sounds not very interesting that it is a three-dimensional perovskite, but if you have a less or more cubic perovskite, you know that there is a perovskite condition, and there is an upper limit of the size of the cation. Because you have a three-dimensional structure, this size is limited. And if it is too big, you need another structure, because otherwise the cation will not have the right space. Another point, methyl ammonium is not a sphere. That means if you try to describe it in a systematical way, you know that you cannot use just the radius, but you know it is a certain shape and it has an interaction. A sphere has no directed interaction to its surrounding, and we know that methyl ammonium cations have a direction and an interaction according to the formation of hydrogen bonds. Finally, lead is toxic. So maybe you can substitute it or reduce the amount of lead. And we could show that there's another nice material which shows some of these aspects that I have mentioned here. Our general idea was first to start with additional organic cations. And one example which was successful was the addition of guanidinium. And this organic cation is significantly larger than the methylammonium, and it has a significant interaction according to the formation of hydrogen bonds, and it's less or more a disk. It's not a sphere. We could synthesize it under the usual conditions, and we found that it is the only crystalline compound is a layer structure with 3 cations, 2 lead, and 7 anions. The crystal structure is, in my view, a quite simple structure. It's a so-called 2D perovskite according to the direction 1, 0, 0. If you imagine the cubic structure of the perovskite, you just do a slice of the cubic structure according to the crystallographic direction 100, following the A lattice parameter, and now you combine 2 of these layers and the story is complete. It should be mentioned that we get dark red crystals. That means we have a first impression of the band gap. The best band gap for the disolar cell is about 1.75 eV. That depends on the maximum efficiency of the solar cell, and we see that with the dark red single crystals we are a little bit above. That means the band gap is a little bit larger. You see, 2 of these layers are combined to a double layer and the octahedra are rotated. This is important because the optical properties and following that also the other physical properties demand this type of distortion, because that's good for an efficient absorption process. And you also see from this picture that the cations have an influence on the stability. This is the methylammonium. You see one is oriented in this way, the other here, and the rotation of the octahedra fits perfectly to the size of the voids, and the 2 other cations also fit perfectly to the other cations. We see that we have 2 different modifications. There's a room temperature form and a high temperature form. The high temperature form is more symmetric as we know it, and it depends on the rotation of the organic cations, and the stability is better than for the normal methylammonium iodide. We investigated the thermal properties, could show that there are several phase transitions, and finally here the decomposition into the normal methylammonium lead iodide and guanidinium iodide at about 200 degrees Celsius. That means the upper thermal stability of our compound, and we have a phase transition around 50 degrees Celsius which corresponds to this transition, but it doesn't change the optical properties. Well, we could show that the active layer the thermal stability was checked by the X-ray investigations. It's quite clear. Now it works again. Yes, we investigated the layer, could show that it is indeed, according to the calculated and the measured X-ray pattern, we have indeed as active layer our 2D perovskite. We could show that the microstructure depends a little bit on the optical impression. There are rough regions and shiny regions, but they all have the same composition. And we did a formation of the layer by addition of ether as an anti-solvent. That means we dissolve it in an organic solvent like DMSO or something like that, and we precipitate it on the device by additional ether. And it's remarkable that it works already at room temperature. Normally you need 50 or 60 degrees Celsius to precipitate the methyl ammonium lead triiodide sample. We have a red shiny layer that corresponds nicely to the optical spectrum we have measured, so we can be sure that the active dye is indeed our compound and nothing else. We built up a device in collaboration with our colleagues from the Fraunhofer Institute for Solar Systems. That means we have a glassy substitute. Thanks. We precipitate mesoporous titanium dioxide at our perovskite layer with a thickness about 300 to 500 nanometers, something like that. Additionally, we do a p-conducting organic layer to get the charge separation, and we back it with a gold electrode. That's the complete device, and we could show that it really works. We have measured the work function, we have measured the charge transfer to the mesoporous titanium dioxide layer, we have measured the optical properties, could show that we have an excellent quantum yield for the photoluminescence, and we had indeed a device that works. The first try was about 3% efficiency, and the important point, it really works with only our dye, because that's not always clear if you have the combination of different cations, which compound is really the active compound. Another example, I know that I should come to an end, but I will come. Some years ago, 2 years ago, there was a nice WIP paper in Angewandte, and it was interesting because they stated that the moisture tolerance is better if you add a little bit of thiocyanate. And then they have published these wonderful X-ray diagrams, and my postdoc Michael Daub said, it's bullshit. And if you are a little bit familiar with X-ray patterns, you know that he was right. The published values are just wrong. So he said, I do it by myself. He did. He showed that the real composition is 2, 1, 2 plus 2. That means the composition is not a normal perovskite ABX3, but A2BX4. And he could show that it is also representative of a 100 perovskite, closely related to the structure of the well-known calcium tetrafluoronickelate. The surrounding is quite simple. You have in the plane the linear coordination with lead and iodine, and the terminal positions are occupied by the pseudo halides, and so we had to publish corrigendum and addendum in Angewandte. And you see, it's indeed, these are different compounds. We could characterize it with the usual measurements. Then we thought, oh, why not guanidinium? It's an ugly work because the stuff has the wrong color. We do some structure work, could show how they are connected. We see 1, 2, 3, 4 different modifications. We determined them all, but as you see, the slightly frustrating comment, we didn't build a device with that because the band gap is too large, and it's just to show we can do it, but it's not very successful. The idea, or the general idea, to have an influence on the dimensionality of the corner sharing octahedra in interaction to the organic cations was shown by the combination of guanidinium with formamidinium, or with the abbreviation TU, means that's thiourea cation. Now, that's a new cation we introduced to this perovskite structure, and we could show that we get samples which have a crystal structure which are so-called 210 oriented perovskite. That means the cutout of the structure of the perovskite follows now the direction or the layer 210. And it was the first example, but it's also not useful. And the last story is the most interesting story. You should always keep your interesting things to the end. By introducing this protonated thiourea into this chemistry, we could show that indeed the idea to separate the three-dimensional structure of the original perovskite by the special demands of the coordination of the second cation leads to a well-defined series of different structures. I've shown it with these scissors that you may cut the three-dimensional structures in appropriate layers, and we could characterize all of them. That means we have a continuous transition from the three-dimensional to the two-dimensional structure. We could continue it from a two-dimensional structure to one-dimensional structures. That means we can cut pieces from the layer structures to trimeric units, to single chains, or if we only have the thiourea compound, this is an ammonium chlorocadmate type, which is a different type of perovskite structures where we have linear structures by double chains of these octahedra. And yeah, I know, I come to an end. The optical properties show clearly that the extent of connection correlates to the color. That means the more edge-sharing lead iodine octahedra we have, the smaller is the band gap and the closer is the color to the black color. We could do the measurements and we measure the optical band gap, and we also, you see it's really perfectly, it goes the whole series from black to nearly colorless. And we could show that the band gaps correlate clearly with the share of the edge-sharing octahedra, and we have seen that the excitones, which are an essential property of the two-dimensional perovskites, is also visible in all these systems. So we could build a device with quite good properties, and especially the efficiency is around 10%, and it's a long-term stable compound. We could draw all these compounds in a diagram and show that they are on a line in combination of our cubic perovskite with the additional iodide of the organic cation. So they are on this line, and all the other compounds which are described as derivatives of the Rutles and Popophasen are on another line within this diagram of composition. So we are at the end. Thanks first to the auditory to listen all these things, and to all my co-workers, which are as a part of the PhD thesis or as a postdoc, which do the investigations on these results. And thanks again. Only 5 minutes, too long. No. But the reason was the long introduction that you gave.
Okay. Very impressively diverse presentation of yours.
Oh,
Questions for Harald?
I guess I killed the system.
Black button.
The black button, they all are black, I guess.
No, I think press this. Never mind. Linda.
That was very nice. The degree of dimensional control you have.
Yeah, it's one of the most pictures I've ever saw in my scientific career. That it really works.
Yeah, that's great. I would assume, though, that you really want more of a three-dimensional structure for the photovoltaic device rather than a 1D or a 2D, because you want to decrease the anisotropy, not increase it. Is that correct?
One-dimensional systems are just basic research.
Okay.
So we just can skip it. according to application, you just look on the color of the crystals and you say it must be at least dark red or smaller band gap. And all the other things are just to give to have an idea how it works. Because we would like to understand the demands of the organic cation, that we know what an influence is there. You are absolutely right. For the applications, the intermediate between 2D and 3D is important because, as I pointed out at the beginning, the 3D perovskites are extremely limited in the possibilities to modify. You have a rigid framework, and the size of the cation is limited by the distances lead iodine. So you always have a lattice parameter about 6.4, and that's just the doubled distance between lead and iodine. If you go to layer structures, you have a free parameter, less or more.
It turned out to be very efficient that I've seen in the literature. Why is that?
It has an influence on the charge transfer. And if you, I didn't comment it too much, you have to precipitate the layer on the device. And two-dimensional 2D perovskites are anisotropic within itself. And you always need a charge transfer process. And if you have a pure two-dimensional systems, it's difficult to come over the gap between the layers. But depending on the microstructure, there's a conductivity between the different layers, and the contact is better the thicker the layer is. If you have a very thin layer, the probability of a broken contact between the layers increases. So obviously there should be a certain thickness of the layer. And I guess you have something quite close to a three-dimensional perovskite. There's some work of Kanatzidis in this field, and we are very similar with these things that we do. And he said he arrives efficiencies around 15% with his two-dimensional systems. But these layers that he has contains 5 layers within the lead iodide part. So it's not yet understood why. Obviously, the excitones have a certain influence, and it seems to be good for the charge separation that you have these layers. But it's not really clear. Nobody knows really how about the contact between your dye and the oxide, like titanium oxide or whatever you use, is really made. Also, the contact between the P-conducting layer, which we use this spiro stuff, and depending on what you use as a material, maybe graphite or carbon nanotubes or what else, there is a difference of the absolute energy. What was the name? The energy level of the electrons. You always have a certain gap, and if the gap is too big, the efficiency is very low, and if it's too small, the efficiency is also very low, so it must be optimized. And we know that our absolute energy of the electrons is not yet the best. So it's in between. We know these perovskites since about 3 years. During the last 1.5 years, the low-dimensional systems became more and more interesting because they are tunable. For example, the substitution with cesium and formamidinium, we have a system containing 3 different cations, and it's very difficult to have a well-defined process for the precipitation of a well-defined layer if you know that the concentrations vary during the ongoing precipitation process. And it's very difficult to steer it if you have so many components. And I guess with 2 organic cations, it's possible. But with 3, or additionally with a variation of the halide, it's very difficult to get reliable results and long-term stabilities. So that's...
We can probably discuss more at lunch
Yeah.
about the long-term stability. But
Yeah.
I understand that the voltage hysteresis from the halide migration is a real problem. Joachim Meyer produced a nice paper on that a few years ago,
Yeah.
seemingly showing that the there was actual
Yeah.
migration of the halides. And is
Yeah.
that suppressed by the thiocyanate?
I agree that small amounts of thiocyanate give a better stability against hydrolysis, but probably not because a substitution within the structure. Because I don't know any example where you have the substitution of iodine by thiocyanate. No. I don't know any example. No. Nevertheless, small amounts can change the way of the precipitation. And for example, it is very well investigated for the case of the substitution of iodine by chlorine. No. And in the first paper and many other papers, it is stated that there is a solid solution. That's impossible. But if you look for the process of the precipitation, then it has a strong influence on the kinetics, no? And that's why it is an influence on the microstructure of the layer of the methylammonium lead iodide, which is the same structure, same compound, but in a different morphology. So the influence is on the morphology, and that's why I was a little bit hesitating with these things here at the end. It is well known that with a slight addition of this urea, you have a positive influence on the stability against hydrolysis. So I'm not sure that it is really this compound here which is responsible for these properties. And that's why I pointed out for our first example that is really our red compound which produces this 3 or 4% efficiency. This is not clear in this case because the characterization of these layers is extremely difficult. Because if you do an X-ray investigation, you only investigate the small layer with quite bad, or not, in my opinion, with limited quality of the X-ray diffraction. And according to the common building principle, many reflections have the same position and the same intensity independent from the layer thickness, because it's always the same parameter. It's given by the structure. So the characterization is very difficult to say, yes, indeed, this compound is responsible for the properties. And that's why we did all these optical investigations, because the optical spectrum is very sensitive. And we have shown for some other examples that we can obtain mixtures of both spectra if we have both compounds on our layer. So we have a quite good tool for the analysis of the really active layer by optical spectroscopy. But for that purpose, we have to fix it for a well-defined compound, that we know which peak comes from which compound. That's why we do the detailed investigations on the crystal structures, to transfer this knowledge on the applied systems. I'm quite sure that well-defined two-dimensional systems are not the best material for an efficient synthesis of the disolar cell. But we should know how it works to have an idea how we can influence the process.
Okay, we should probably move on. Let's thank the speaker again.